Well, this video segment is going to describe the forces involved with circular motion. Now, you should already know something about circular motion. I know in my course I covered that several chapters ago. The most important thing is to remember that speed and velocity do not mean the same thing in physics. So we can have something moving in a circle at a nice steady speed that is still changing its velocity. And that's because velocity includes direction information. And so if you're moving in a circle, you're definitely changing your direction all of the time. So if we use the phrase uniform circular motion, that means steady speed, but still accelerating or changing your velocity. That acceleration is always pointed towards the center of the circle. So if we take, for example, something moving like that, so I draw little motion tails on there, and so we're implying that we're going in a counterclockwise direction, then we have a velocity that is forwards. We mark it with that vector. But we have an acceleration vector that points towards the center of the circle, like that. Well, if we're accelerating, then we also have an unbalanced or net force acting on it. And so Newton's second law, which says that the net force will equal the mass times acceleration, this implies that we will always have a net or unbalanced force for anything moving in a circle. That includes moving in a nice uniform circular motion or even something that's changing its speed. And that net force could change depending on the particular situation. What's causing the net force can be different. I'll show you some examples here in a little picture. There's several pictures. Here's a bunch of examples of things moving in circles. In the first case, we have a satellite orbiting. And what would be the thing pulling towards the center? Well, that's going to be the gravitational pull of the Earth. In the second case, when we whirl around a heavy ball, this is like the hammer throw in a track event, then we have a chain, the tension of the chain. And if you look at the next three, those are people that are moving in circles, and in each case, they have to maneuver the position. So, for example, the skier has to kind of lean inward so that the board that he's on will push outward. That means the water is the inward force. In the case of the motorcycle riders, they have almost a wall that they're riding on there. The inward force is the normal force pushing on the wheels. And in the last example, where those cars are, if that's a flat track, then we're going to rely on friction. So friction can be the inward force that allows circular motion. And this is true for you too. As you round a curve, let's say on the road, if you don't have good friction, or we call it traction sometimes, then you're not going to be able to negotiate that curve. In the wintertime, if things get icy where you are, if you don't have friction, there's no way for you to negotiate a turn, and you can't move in a circle. You end up going in a straight line, and often your car ends up moving where you don't want it to move. So there's some examples of how we move things in circles. And there's no way that you can ever move in a circle without having that inward force. So remind you of something from kinematics, and that is that we call this acceleration centripetal because it's pointed towards the center, which is sometimes just called centripetal for short. And that is normally easiest to calculate by doing v squared over r. If you have the actual speed, the speed is v. You can also use a different form. Omega squared times r is also equivalent to the centripetal acceleration. That's if you have the angular speed. But in either case, that would get you the net force. Now, let me show you an example of a real application of this. So perhaps we have an amusement park ride where the track makes a circle, and they never actually are perfect circles. I'm just approximating here to make the physics a little easier. But if we have this car down at the bottom, typical question might be, all right, if this car is moving rightward, so we're making a counterclockwise circle, and they might say, well, what is the normal force of the track on the wheels of the car at that point? So you approach this just like I approach any Newton's law problem, and that is, first draw your forces in. So a lot of times when people are asked about a particular force, they forget that there are other forces involved. But of course you have a gravity force pulling down. You'd have to know the mass in order to find that out. And you would also have the upward push of the track on the wheels, and that we'd call the normal force. And if that's what you're after, you have to know how these two relate to each other. So in this position down here, because we're at the bottom, our acceleration is upward or towards the center. So what would a Newton's second law equation look like down here? It would say that the unbalanced force, that would be the normal minus the gravity, however much bigger normal is than gravity, will equal the m times the acceleration v squared over r, where r is the radius of that circle that's being made. So that would allow you to solve for the normal force. Well, what happens up here? At some point, the car is upside down. And what's different there? Certainly not the weight. You're not going to lose weight by going up there. But the normal force is now directed downward. So your Newton's second law equation looks a little different up there. Now the net force is not the difference in those, but the sum of them. So Fn plus Fg equals mv squared over r. You're going to get different normal force. This is the sensation you have as you ride like this, is you can feel that normal force as how the seat pushes on you and you push on the seat, because that changes in the course of the ride. And I always like to look at the situation over here on the side, because at some point we're going to be heading up there. And then while we have the gravitational force down, now the push of the normal force is inward or leftward. So what's going on here? Well, we have a net force in two different directions. So we have the normal force responsible for the centripetal part of the acceleration. And so that alone would be the mv squared over r. And what is gravity doing? Well, if we're on our way up and gravity is acting down, then at this moment, you're actually accelerating in the tangential direction. So the net force in that direction would not be mv squared over r, but tangential acceleration, we would denote a with a subscript t. And a lot of times if you go back to the, at least in my text, the kinematics chapter, we have an expression for the tangential component, which is alpha, the angular acceleration, times r. I'll kind of set that off because that takes the place of the tangential acceleration. So that might be a possibility. They could say, you know, what is your momentary angular acceleration at that point? So everything is kind of customized depending on where you are in the course of the ride. So every circular motion problem, of course, is a little bit different. And if you look at, back at some of those pictures I showed you with other examples, for example, friction might be your only force keeping it moving in a circle. So you'll have a different expression involved. You could get a coefficient of friction involved. One of the common questions is, how fast can you go with a particular coefficient of friction? And it really all starts with what you saw here, Newton's second law from a diagram that you create about that situation. So I think we'll stop it there. That gets you enough, hopefully, to get you started, and you can apply it to the specific examples you find in your work. Good luck.